Let us solve a problem using Milne's predictor corrector method. We are asked to solve differential equation dy by dx equals x minus y square in the range x belongs to closed interval 0, 1. We are asked to take step size h equals 0.2 and we have the initial condition y of 0 equals 0 or y equals 0 and x equals 0, which is of the form y of x naught equals y naught. In order to start with the first approximation, we will use Picard's method. Since no methods are specified here, any of the methods can be adopted. Here we have adopted Picard's method. We have using the formula of successive approximation by Picard's algorithm. The formula is y equals y naught plus integral 0 to x f of xy into dx. We have y of 0 equals 0 here and y1 equals y naught plus integral 0 to x dx is the first approximation. This first approximation is obtained by giving y equals 0 in this formula. We have f of xy equals x minus y square, and in this expression of f of xy, when you give y equals 0, we obtain f of x0 equals x minus 0 square. That is, at y equals 0, we have f of xy equals x. Therefore, in computation of first approximation, y1 equals y naught plus integral 0 to x dx. By usual integration, we have y1 equals x square by 2. Notice that y naught equals 0, which is already given in the boundary condition or the initial condition. In order to perform the second approximation, what we do is, in the expression of f of xy, we will replace y using y1. That is, we put y equals y1 in the expression of f of xy. We have y1 equals x square by 2 as per the first approximation already computed, and hence we have when y equals x square by 2, f of xy becomes x minus x square by 2 the whole square. That is, f of xy equals x minus x raised to 4 by 4. Thus, we have second approximation y2 obtained by giving y equals x square by 2 in the expression of f of xy equals integral 0 to x minus x raised to 4 by 4 into dx. By usual integration, we obtain y2 equals this function. We have third approximation evaluated using y equals y2 to be substituted in the expression of f of xy. That is, we have f of xy at y equals y2 becomes x minus x square by 2 minus x raised to 5 by 20 the whole square. Thus, we have y3 equals integral 0 to x minus x square by 2 minus x raised to 5 by 20 the whole square into dx. By usual integration, we get y3 equals this function. Now we have found first approximation, second approximation and third approximation using Picard's method. Now we have to find out initial values required for Milne's method. We have x values following the step size h equals 0.2. Since the range for x is defined as closed interval 0 to 1 and step size is h equals 0.2, we have to start with x naught equals 0, x1 equals 0.2, x2 equals 0.4, x3 equals 0.6 and so on. We have x naught equals 0 and y naught equals 0, which follows from the initial condition. F naught is function's value at x naught y naught, that is, f naught equals f of 0 0, which equals 0. We have x1 equals 0.2 and y1 equals x square by 2 from the first approximation. In this expression of first approximation y1 equals x square by 2, we will give x equals x1. Thus, we have y1 equals 0.2 the whole square divided by 2. Using these values of x1 and y1, we will compute f1, where f1 equals f of x1 y1. Thus, we have f of x1 y1 equals 0.1996. Similarly, since x2 equals 0.4 and y2 equals x square by 2 minus x raised to 5 by 20, which is obtained from the second approximation, in this expression of y2, we will give x equals x2. Thus, we obtain y2 equals this expression. Having found value of y2, we will compute f of x2 y2, which equals f2. Thus, we have f of x2 y2 equals 0.3937. We get f of x2 y2 equals 0.3937 by giving x2 equals 0.4 and y2 equals 0.0795 in the expression of f of xy. Now we will evaluate f3, which is f of x3 y3. We have x3 equals 0.6 and y3 can be evaluated using this expression of y3 which follows from the third approximation from the Picard's method. In this expression of y3, we will give x equals x3, that is x equals 0.6 is substituted here in the expression, giving value of y3 as 0.1762. Having found x3 and y3, we have f3 equals f of x3 y3 which equals 0.5689. We have the predictor formula for y4 given by y4 equals y0 plus 4h by 3 2f1 minus f2 plus 2f3. We have evaluated f1, f2 and f3. Also we have y0 equals 0. Giving all the particular values of f1, f2, f3 and y0, also h equals 0.2, we will get the predicted value of y4 as 0.3049. This value of y4 corresponds to x equals x4. We have x4 equals 0.8 which is at 0.2 distance, or which is at step size 0.2 distance from x3 equals 0.6. Since we have now found y4 using predictor formula, we can now find out f4, that is function's value at x4, y4. We will give x equals 0.8 and y equals 0.3049 in the expression of f of xy. Thus we have f4 equals 0.7070. Any error that has occurred in the computation of y4 while using predictor's formula can be corrected using corrector formula. We have the corrector formula for y4 given by y4 equals y2 plus h by 3 times f2 plus 4f3 plus f4. We have y2, f2 and f3 values computed. Value of f4 was just computed having found the predicted value of y4. We had f4 equals 0.7070. Using these values and h equals 0.2, we will compute y4 equals 0.3046 using corrected. Using predictor formula, we had obtained y4 equals 0.3049. Now using corrector formula, we have obtained y4 equals 0.3046. And this latest value is the corrected value. Using this value of y4, we can now update value of f4, that is at x equals x4 and y equals y4 which equals 0.3046, we have f4 equals 0.7072. Using this value of f4, if you again apply corrector formula, that is when you again compute y4 using the value of y2, h, f2 and f3 as in the previous case, but f4 is now updated with the latest value 0.7072. Here in this formula, when you give all the particular values as in the previous case along with f4 equals this value, you see that y4 is again obtained as 0.3046. Notice that we have used corrector formula twice. But still value of y4 is the same. Thus we can confirm with the value of y4. Now let us predict the value of y5. We have this formula to find out y5. Giving particular values of y1, h, f2, f3 and f4 equals this value, in this formula we will get y5 equals 0.4554 and this value of y5 corresponds to the value x5 equals 1.0. We had x4 equals 0.8 and x5 is 0.2 distance from x4. Following the step size h equals 0.2. That's how we have obtained x5 equals 1.0. Since we have x5 and y5, we can compute f5, giving x equals x5 and y equals y5 in f of xy equals x minus y square. We obtain f5 equals 0.7926. Now we will use this value of f5 to correct the formula or to correct the value of y5 using corrector formula for y5. The corrector formula for y5 is given by y5 equals y3 plus h by 3, f3 plus 4f4 plus f5, where f5 whose value is obtained as 0.7926 from this step and f4 whose value is updated as 0.7072 will be used, and hence we compute corrected value of y5 as 0.4555. Since we have obtained new updated value for y5, we will again compute f5. We have at x equals x5 and y equals 0.4555, we will get f5 equals 0.7925. In the expression of f of xy equals x minus y square, we are giving x equals x5, which is 1.0, and y equals 0.4555 to obtain f5 equals 0.7925. Using predictor formula, we had obtained f5 equals 0.7926, and now using corrector formula, we have obtained f5 equals 0.7925. Now we will again apply corrector formula, but here when you apply the corrector formula second time, we will have f5 equals 0.7925 instead of the previous value 0.7926. That is, using this updated value of f5, again you will make use of this corrector formula with y3 equals 0.1762, h equals 0.2, f3 equals 0.5689, f4 equals 0.7072 and f5 equals 0.7925. Thus we again obtain y5 equals 0.4555. With this we confirm that y5 takes this value itself. Now this value of y5 corresponds to x5 equals 1.0, that is at x equals x5 equals 1, we have the value of y is this value, which is y5. Notice that in the question given x ranges from closed interval 0 to 1, we have found value of y at x equals 1, which is the upper bound. Hence, using Milne's predictor corrector formula, we have found value of y at x equals 1 is 0.4555.